Thanks, Vanessa. So I'd like to start by thanking Yasu for putting together this entire workshop. Also, Chisato Mori. It's been a real pleasure. So thank you. This is my first time in Japan, so it's great to be here. So I'll be talking about Viator-Schrips complexes of manifolds is my title. Uh, Vanessa was sort of teasing me a little bit. Really, I'll be talking mostly about spheres. Um, But I wanted to start by saying some things about AATRN. So maybe I'll talk about AATRN for several minutes or 5 minutes or so, in part just because many of the organizers of APATG, the Asia Pacific analog, are here. So AATRN is an online network. We have weekly talks. It's co-organized by myself and Hanka Dalpolz Karizka and Teresa Heiss. Barbara Giunti recently joined the team, Sarah Klishnik, and Bastian Rieck. So it started in 2014 or so before I was involved. And then I joined in 2016 or so. Sarah Klishnik and I were the two organizers when the pandemic hit. And so we really invested a lot of energy and attention and added more folks around that time. But it's been quite successful. So we now have a YouTube channel. We have over 600 videos on it, about 18 hours watched per day, 8,000 subscribers on YouTube. One little known aspect of AATRN is that you can just contribute a video. So if you record a video, or if a student of yours records a video, it could be a tutorial or a research talk, send it to us and we'll post it on the YouTube channel and it'll get viewed. Let's see. So Sarah is successfully stepping down after our 10-year anniversary conference in Chicago. I plan to step down the following summer. So we had a failed executive director search last year. So we got in touch with some people. We invited 3 people to take over my role, and we got declined. What we're doing this year is we're splitting my role into 2. So Bastian Rieck will be taking over running the weekly seminar, and I'll hopefully step away from the Wednesday seminar. And I'll try to be more of an external facing director for a year. And then I hope to step down, to pass it on to others. I'd like to thank Emerson for serving on our speaker selection committee for the past couple years. And Woojin will be joining the speaker selection committee, which is fantastic. Yeah, any questions about AATRN? All right. All right, so the topic today will be Viator-Schrips complexes. So X is a metric space, and you need to choose a scale parameter R or allow a scale parameter R to vary. And the Viator-Schrips simplicial complex, well, it has vertices, edges, triangles, etc. Your vertex set is just every single point in your metric space. So here on the left, I have a metric space. Maybe it's equipped with the Euclidean metric in the plane. It has 20 points in it. So even, at an epsilon scale parameter, the RIPS complex has 20 vertices in it. And then the simplices in the RIPS complex are all finite subsets of diameter, say, less than R. So you add an edge whenever the 2 points are within distance R of each other. And the diameter of a simplex is just the length of the longest edge. So whenever you have the 3 edges forming a triangle, you add in the triangle. Whenever you have all of the edges forming a tetrahedron, you add in the tetrahedron, right? So even though this metric space was in the plane, you do get tetrahedra, for example. Right? That's not the case with the alpha complex. So if your data actually lives in the plane, don't build a RIPS complex, build an alpha complex. In higher dimensional space, you might like to build the alpha complex or the Czech complex, but at least currently the RIPS complex is more efficient to compute the persistent homology, say using RIPSer software. All right, and then the idea of persistent homology is that you might approximate the shape of this data by allowing the scale to increase from small to large. And you might trust larger holes that persist for a range of scales, perhaps more than smaller holes that don't persist as long. Questions so far? Okay. So this picture is a Rips complex built on top of a finite metric space, but we'll also consider Rips complexes built on top of infinite metric spaces. So there, you have an infinite number of vertices, and you might have simplices of arbitrarily high dimension. So the stability results for Rips complexes, proven by Fred Chazal, Vin De Silva, and Steve Udo. Well, it says more than this. It gives a Lipschitz bound, but it says that if two metric spaces X and M are close, then the persistent homology barcodes you get by computing this nested family of Rips complexes are close. So in this talk, X will often be a subset and M will often be a manifold. So the question that we'll consider is, for M a manifold, what can we say about the Rips complex of the manifold? All right, so I might draw some on this. I should have paid more attention during the knot theory talks. No, I did. Okay. So, the nicest data set you might have is if your data set is sampled from a manifold, right? So in black, I have a manifold, and then in blue, I have some data sets. Okay. And, more generally, your data might be sampled from, not a manifold, a stratified space, and maybe it's noisily sampled. Okay. But the easiest situation would be you have a manifold, and then you have a data set sampled that's perhaps even a subset of it. Okay. Now, in the limit, as you sample more and more points, right, the persistent homology of your data set is converging to the persistent homology of the Rips complexes of the manifold, right, by the stability of persistent homology due to Fred, Vin, and Steve, right? So this question about Rips complexes of manifolds, one way to motivate it is it's just the limiting object in the nicest data context you can imagine, right? So the very nicest data sets, think of them as limiting to manifolds. So in reality, when we distribute this Ripser software to people and people are using it, in the limit, we're asking people to approximate Rips complexes of manifolds. But the theory of Rips complexes of manifolds, we still know very little about. That's one way to motivate this question. I think another potentially better way to motivate this question is Rips complexes are fairly natural sort of configuration spaces or parameter spaces you can build on top of a space. You're looking at all subsets of bounded size, where size is measured by diameter for the Rips complex or by the radius for the Čech complex. And so you might expect, considering subsets of bounded size, right, that might encode important aspects of your shape. So recently, we've seen some connections to equivariant topology, combinatorial topology, metric geometry, Gromov-Hausdorff distances, as you'll see a little bit more of later on in the talk. All right, so one of the foundational results is that if you have a Riemannian manifold and you build a Rips complex at a sufficiently small scale, then you recover the homotopy type of the manifold. Okay, so you have a manifold, maybe the circle. It's a one-dimensional manifold if it's a circle. And then when you build the Rips complex, you immediately get simplices of arbitrarily high dimension, right? Because if my scale parameter is 3 inches, well, anytime I have a million vertices, right, within 3 inches, then I have a simplex with a million vertices. Okay, so these Rips complexes of manifolds are very complicated simplicial complexes. They're infinite dimensional. So it was a big achievement of Hausmann, and the proof is difficult to get this homotopy equivalence. Okay. Only for small enough scales. Hausmann's result has been extended by Lotchev in 2001, who proved that you don't need to build the Rips complex on the entire manifold. You could build the Rips complex on a nearby subset, potentially a finite subset, and still recover the manifold. Okay, so in this data context, you could build a Rips complex on X and still recover the homotopy type of the manifold. And tomorrow we'll see a talk by Sushavan Maji. So he's considered extensions of Lotchev's theorem to non-manifold spaces. Questions? All right. I think the main connection to applied topology is at small scales, right? You're often trying to recover the space at small scales. I study a lot Rips complexes of manifolds at larger scales. I mean, in practice, when you use Ripser software, you do let the scale go as high as computational limits, right? All right. So one result with Michael Adamaszek is we understand the shapes, the homotopy types of Rips complexes of the circle at all scales. So here's a statement of the result. The Rips complex of the circle is always an odd dimensional sphere. Or once the scale's larger than the diameter of the circle, then you have every possible simplex, and then it's contractible. Okay, so for small scales, you recover the circle up to homotopy type, as Hausmann's theorem says you must. Okay, and then these critical values tell you where the homotopy type changes. So when you plug in k equals 0, k equals 1, k equals 2, k equals 3, you get these values 0, 2 pi by 3, 4 pi by 5, 6 pi by 7, etc. Okay. And in these intermediate regimes, the homotopy type is an odd dimensional sphere. So you recover the circle for a while. Then when these equilateral triangles fill in, it doesn't become contractible. It actually becomes a three-sphere, as I'll talk about a little bit. And then when these regular four simplices appear, it becomes the five-sphere. So you get all odd spheres for smaller and smaller windows of scales until it becomes contractible. And you recover similar homotopy types if you have just, say, 100 evenly spaced points on the circle, or 1,000 points sampled uniformly at random on the circle. Questions about the statement? Okay, let me discuss the intuition for this three-sphere on the board. Ah. All right, so here on the left, I'll have the circle and we'll build the Rips complex of the circle, okay? And then here on the right, I'll have a model for how you should think about the homotopy type. All right, so at small scales, you have edges, triangles, tetrahedra of arbitrarily high dimension, but they live near the circle. In particular, at small scales, if you projected this Rips complex to the plane, if you considered the shadow, you'd get a two-dimensional annulus, right? You miss the origin, so you could radially project onto the original circle and you recover the circle up to homotopy type, okay? Even though it's an infinite dimensional circle. Now, here I've drawn an infinite dimensional solid torus for you, but what I want you to think of is of a single 3D solid torus sitting here in this room, okay? So up to homotopy type at small scales, this infinite dimensional solid torus is really just homotopic to a 3D torus, solid torus sitting in front of us, right? All right. And then what happens is that at scale 2 pi by 3, finally, you first have simplices whose projection to the plane contain the origin, okay? So at 2 pi by 3, for the first time, here's a set of diameter 2 pi by 3, right? And its projection to the plane now contains the origin. So it looks like we filled in the hole, right? If you only glued in one equilateral triangle, you would just fill in the hole and you'd be left with something contractible, right? You just fill in one disk right here. But in reality, you don't have just one equilateral triangle, it appears. You have the whole circle's worth, okay? So you have this nearby equilateral triangle, which I want you to think of as a nearby disk that you've glued on. and you have another nearby equilateral triangle, which I want you to think of as another nearby disk that you've glued on. Okay. And so glue on all these disks. This disk passes through the point in infinity. Okay. And eventually, when I rotate these equilateral triangles around, I get back to where I started. Okay. So I'm gluing on these disks. Eventually, I get back to the disk where I started. Okay. So what I have here is S3. You can think of as R3 union the point at infinity, right? The 1-point compactification of 3D. And I've built for you 3D plus the point at infinity as this union of two solid tori, right? So you could write S3 as take one solid torus, glue it to another solid torus, and you glue it along the boundary hollow torus. Okay. So this is analogous to the Heegard splittings that we saw yesterday in Professor Shimokawa's talk, right? So he was looking at higher genus Heegard splittings. I think sometimes of the three-dimensional torus instead of the three-sphere. But this is just the genus 1 Heegard splitting of the three-sphere, where you write the three-sphere as two solid three-dimensional tori, right? For us, one torus was this infinite dimensional part coming from the local simplices, and the other torus was a three-dimensional torus coming from all triangles. Do you see that? Okay. Another description we'll see of S3 in the talk is the join of a circle with itself. So when you join on more and more circles, you get odd spheres. So your two circles here would be take one circle that's just the center of this solid 3D torus, and then take another circle which is passing through the point at infinity. Okay, and if you take the join of these two circles, right, you fill out all of 3D plus the point at infinity, sort of using all of these blue disks. Questions for that intuition? All right, so that is not how the first proof went, right? The first proof was using combinatorics, really. We learned as much as we could about Rips complexes of finite subsets of the circle, and then we wrote the Rips complex of the entire circle as a union or a colimit of these finite subsets, and then we used properties of homotopy colimits. My student Michael Moy has a more geometric proof of these homotopy types. He's using the slightly different topology, the Rips metric thickening. And you'll see more about that, I think, in Nikola Sadovek's talk tomorrow. In my talk today, I won't distinguish between these two different topologies on the Rips complex. So we saw how when you glue on a circle's worth of triangles to the circle, you get the three-sphere. And then similarly, when you take the three-sphere and you glue on a circle's worth of four-dimensional simplices, you get the five-sphere. Okay. You're actually just joining with one more copy of the circle. Questions? So joint with Nikola and Evgenia and Michael and Adi, we recently figured out the equivariant, S1 equivariant homotopy type. So the circle acts on itself by rotation, and then that induces an action of the circle on the Rips complex. Okay. This is an infinite dimensional space, but here's the finite dimensional model of the odd sphere that preserves the S1 action. So these subscripts mean that as you rotate the first circle around once, say rotate the North Pole around once, the circle's worth of equilateral triangles rotates around 3 times, right? Do you see that? Because if I rotate the North Pole to itself, the equilateral triangle passes itself 3 times. So that's the structure of the equivariant homotopy type. And then you can deduce the equivariant persistent cohomology from there. These joins descriptions you'll see again. So I mentioned how the three-sphere was really the circle joined with itself. So the first circle was the space we started with. And then the second circle was the circle's worth of equilateral triangles. All right. So it was a join of the original space joined with how many critical simplices did we glue on. You'll see that again. All right, so much less is known about n spheres, and even less is known about more general manifolds. Um, we do know the first new homotopy type, but we'd like to know this first new homotopy type extends for plus epsilon more, and that's not known in general. So what happens for the n sphere? Um, so let's start with the two sphere. All right, so here's my two sphere. I build this Rips complex, so I have edges, triangles, at small scales. None of those simplices contain the origin in their convex hull until you reach this scale parameter, which we call Rn. And Rn is the scale parameter of this inscribed regular tetrahedron. Okay, so the edge length here is Rn. There's a formula for it in terms of arc cosines of -1 over n plus 1. Okay. But at this scale parameter Rn, now this regular tetrahedron appears. Okay. If you only glued in one tetrahedron, you'd make this space contractible. But you're not just gluing in one tetrahedron, you can sort of rotate this tetrahedron around. Okay. So this parameter space, SON plus 1 mod AN plus 2, this is the parameter space of all regular tetrahedra that glued in. So we're talking about the two sphere. The two sphere sits in, n is 2. The two sphere sits inside 3D, right? So SO3 tells you how many ways can you rotate this tetrahedron around in 3D. And then A4, that's the alternating group on a set with 4 elements. That's the rotational symmetries of the tetrahedron. Okay, so that, this is sort of how many ways you can rotate the tetrahedron modded out by the rotational symmetries of the tetrahedron. Okay, so the new homotopy type is, again, the space we started with joined with the parameter space of how many critical simplices appeared to fill the sphere. This proof technique is much more geometric. Yeah. Questions? Yeah, Kelly. Yeah, I sort of used to think this was related to the hop vibration. Maybe it's an analogy, but not a perfect analogy, I don't think anymore. There are these things called Seifert fibrate spaces that I think should be related, but no one's related yet. The action's not free, so take the barycenter of this equilateral triangle. If you rotate the triangle 1/3 of the way around, that barycenter maps to itself. Yeah. Nicola, do you have more to say? Yeah. I should say this was a really fun paper to write because I guess I was the only faculty on this paper, and Michael was my student, and he understood the geometry really well from this paper he did. But then Adi was a student of Alexander Jernishnikov at Florida, and then Nicola and Evgenia were students at the time from Berlin. So they all knew Adi and Evgenia and Nicola all knew, equivariant homotopy theory, right? Which I don't. So, I mean, I try to be honest and understand, every sentence in a paper I'm on, right? And I can't say I met that bar in this paper, right? I tried, but I learned a lot from them and clearly have a lot more to learn, hopefully. All right. So, right. Let me say that a little bit more is known in the case of the two sphere besides this first new homotopy type. So let me talk about that. There's important work by Lim, Okutan, and Mamoli who connected Rips complexes of spaces to neighborhoods of the Kuratowski embedding. Okay, And then this meant that a lot of work that Michael Katz did, Michael Katz was a student of Gromov, trying to understand filling radii of manifolds, applies to Rips complexes. So when you combine Lim, Okutan, Mamoli, and Katz's results together, you get, in the case of the two-sphere, that this homotopy type does extend for epsilon more, and it extends up into this scale of what I called the pentagonal pyramid. Okay, so let me describe this pentagonal pyramid just because I think the geometry is interesting. Okay, so this is 6 of the 12 vertices of an icosahedron. All right, so an icosahedron has 12 vertices. You have the North Pole, the South Pole, and then you have 5 vertices on each of these 2 planes. Okay, and the 5 vertices are equally spaced around the circles that get cut out. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Now, remember in the case of the circle, it was the odd polygons that affected the homotopy type because the odd polygons don't have antipodal points. Antipodal points are at the maximum diameter apart, right? They appear very last, so they don't change the homotopy type. They're, right. So we don't want to include all the vertices of the icosahedron. That includes antipodal points. Those don't appear until the very end, where it's obviously contractible. But take just the North Pole and then these 5 vertices, okay? So in this simplex, this distance is the same as, as these distances, okay? So if I draw this 5 cycle, the 5 cycle has shorter edges, but these diameters of the 5-pointed star, those distances are the exact same as this distance, okay? So Katz proves that this current homotopy type persists up until this scale, okay? After that scale, we don't know what happens, right? But you should be gluing on parameter spaces worth of these 5-dimensional simplices, right? This has 6 vertices, so it's a 5-dimensional simplex. A 5-dimensional simplex, its boundary is a 4-sphere, right? So you want to know how that 4-sphere boundary is attached onto the space you had before. And we do know pi4 of the space we had before. Okay, so pi4 of the space is z mod 3z, right? So there's sort of up to homotopy 3 choices of attaching maps. You know, the previous transition was from the n sphere to this space, and we were gluing on a bunch of these n+1 simplices along their boundary n spheres, and the attaching map was just the identity map, right? This tetrahedron was glued on according to the identity map. Now we should be gluing on these 5-dimensional simplices attached along their boundary 4-sphere, right? And up to homotopy, all that matters is the homotopy type of that attaching map. So no one's tried to work out this next homotopy type, but I think you might be able to write it as an adjunction space, right? Involving gluing on these pentagonal pyramids. Questions about that? Yeah. So this result is written using the geodesic metric on the n-sphere. But if you use the Euclidean metric, it's really the same problem, just because distances increase monotonically, compared to the geodesic metric and the Euclidean metric. So of course you need to change the scale parameters, but once you just change the scale parameter from the Euclidean to the geodesic, it's the same problem. Yeah. Other questions? All right, so a conjecture is that these critical scales are related to the diameters of certain polytopes that Lovash studied, called strongly self-dual polytopes. Maybe I won't talk more about those right now, but happy to chat later. All right, so in recent work, we study the following thing. Exact homotopy types of Rips complexes of spheres is probably hard, and so we're going to try to bound the topology. Now, I'm sort of unhappy with this. I think that even though exact homotopy types are hard, exact homotopy types ought to be studied and should be studied. But Yeah, but we're going to do some bounds. So let me describe the types of bounds we're going to do. So in the case of the circle, we went from the circle to the three sphere to the five sphere to the seven sphere, etc. We're just going to consider the homotopy connectivity of Rips complexes of the n sphere. So the homotopy connectivity of a space is up to what dimension do the homotopy groups vanish, okay? So this space starts as just connected. It's a circle. It's not simply connected. It's not one connected. And then you get the three sphere. That's two connected. The first two homotopy groups vanish, but not the third. And then we get this next space, which is the five sphere. That's four connected. The first four homotopy groups vanish, etc. So for the n sphere, we're going to study this homotopy connectivity. And we give regions of scales in which the homotopy connectivity could be a certain value, okay? So if the homotopy connectivity of the Rips complex of the n sphere is equal to k minus 1, meaning the first k minus 1 homotopy groups vanish and the kth homotopy group does not, then we can give bounds on the scale, okay? And the way we consider the scale is how far away is the scale parameter from pi, okay? So what you get is these intervals of where the Rips complex could possibly have certain homotopy connectivity. So if the Rips complex is, this is the case of the two sphere. So if it's one connected, simply connected, but not more, then the scale has to be in this range. Okay. And then if the Rips complex of the two spheres is two connected, the scale has to be in this range, etc. The ranges on scale are governed in terms of covering numbers. So this is the smallest radius so that you can cover the n sphere with 2k plus 2 balls of that radius. And this covering number is the smallest radius such that you can cover RPN, projective space, with k balls of that radius. Okay. So these covering numbers go to 0 as you increase k, right? So as the connectivity is going to infinity, these intervals are getting tighter and tighter, approaching scale pi. One nice corollary, which is new, is that the homotopy type changes infinitely many times because these connectivities have to be increasing towards infinity and they get arbitrarily large. So that was, as far as we know, not yet known that the homotopy type changes infinitely many times. But now we at least know that. In the circle, how many times did the homotopy type change? It only changed countably many times, right? Even though there's the real numbers are uncountable. The homotopy type only changed countably many times. So that's a good conjecture here. You would conjecture the homotopy type only changes countably many times. That's totally unknown. You would conjecture that the homotopy connectivity is non-decreasing in the scale, right? You conjecture the space only gets more and more connected, more and more homotopy groups vanish. That's totally unknown. So far, these infinite simplicial complexes always have finite dimensional CW complex models, right? So you would conjecture that for nicetif manifolds, right, the Rips complex is always homotopy equivalent to a finite dimensional thing. That's totally unknown. Yeah. Questions? Yeah, Lucas? Yeah. Yeah, so for the n sphere, it's always like a n plus 1 dimensional simplex that first changes the homotopy type, right? For projective planes, RPN, right? For RPN, it's always critical triangles that change the homotopy type of RPN for all n. Yeah, which I think complicates the story a little bit. Yeah, Kelly? Right, so that's this HDIM, right? So yeah, so finite dimensional CW complexes like an n sphere, you could have homotopy groups of unbounded dimension, right? Homotopy groups of spheres are hard. but the homology of a finite dimensional CW complex is bounded. So it'd be nice to have quantitative bounds on up to what dimension is the highest dimension where homology appears. So that's what HDIM is, right? And yeah, I think this is a reasonable problem to try to tackle, try to get an analogous bound on the topology where you're saying, in this regime of scales, we at least know that homology in dimension 100 and above disappears. Yeah, 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 definitely. I mean, let's see, sort of by Hurevich, right? I mean, there's some connection between the first dimension in which homology and homotopy groups appear, right? These are all for the n sphere and above. These are all simply connected. These Rips complexes are known to be simply connected at all scales. Yeah. I mean, even here, for this transition from the n sphere to the first new homotopy type, I think it'd be nice to try to come up with a simpler homology proof, right? So you have all these tetrahedra that fill in, right? And connections between the tetrahedra, right? Can you prove that H2 vanishes, right? So just take an arbitrary uh, two cycle, right? And then show that you could take that arbitrary two cycle and shrink it away to a null homologous two cycle, right? It seems like it should be doable. Yeah, or just prove that one exists, right? I mean, I haven't seen a proof like that, and I think it'd be if somebody could do a proof like that. So take the two sphere, look at this scale slightly larger than this, and then prove that any two cycle is null homologous, right? If you could prove that, I think that tool will then be useful for many other questions. What's up? Yeah, yeah. I mean, this is like a discrete group action. So it's a manifold of the same dimension as SON plus one. All right. This upper bound on connectivity we've known for several years now. The lower bound on connectivity, there's actually a pretty easy argument going back to Meshulam to give this. We just didn't know how to do it ourselves until Yelena Gerbic and Martin Bendersky, they used these lower bounds on connectivity to control the connectivity of Rips complexes of hypercubes. Okay, so we're sort of behind in some of the tools that we're applying. Um, Many of you might know Matt Kale's work on expected topology of random geometric complexes, right? So Rips complexes from points sampled in the plane. He used similar bounds in that work. So I think I might try to go through the proof of this upper bound on connectivity. So we're going to prove that if delta, this distance of the scale away from pi, is bigger than or equal to twice the covering radius in RPN, then the connectivity has to be smaller than this. Okay, so I want to prove one side of this bound. And the reason why I want to do this proof is I just want to point out the connection to Borsuk-Ulam theorem. Okay, so equivariant topology is showing up. So we're proving one side. If delta is greater than or equal to twice this covering scale, then the connectivity can't be too large. So this is the upper bound on connectivity. Okay, so we're proving one side. Okay. So the n sphere has a natural Z2 action. You can just map each point to its antipodal point. And that descends to an antipodal action on the Rips complex. So you map each simplex to its antipodal simplex. Okay. So a Z2 space is just a space equipped with this antipodal action. Okay. Now, if this Z2 space were sufficiently connected, if the first so many homotopy groups vanish, then we'd get an odd map from the K-sphere into this space. So I want to sketch how to do this. I wish I knew this a lot earlier. Okay. So I have a space with an antipodal action, and I'm pretending that the first so many homotopy groups vanish. And I want to show you how to produce a Z2 or an equivariant map in. Okay, so the board is my space. Okay. If it's, I guess, -1 connected, then it has a point in it. Okay. And then it's a Z2 space, so you have an antipodal point. Okay. And so now you've mapped a zero sphere into your space. And you've mapped in your zero sphere in an odd way. All right. I've mapped in a zero sphere into my space in an odd way. Now, if my space is zero connected, then it's connected. So there's a path between those points. Okay. And I can apply the antipodal action to that path. So I reflect that path. And now I get a Z2 map from the circle into my space. You see that? So now I have a Z2 map from the circle into my space. Okay. If my space were one connected, simply connected, then I could fill that circle with a disk. So I fill this circle with a disk, and then I reflect that disk to get a two sphere. And now I have a Z2 map from the two sphere into my space. You with me? Okay. But this is going to contradict the Borsuk-Ulam theorem. We're going to prove that there's a Z2 map from this Rips complex to a sphere of one lower dimension. Okay. And one version of the Borsuk-Ulam theorem is that there's no Z2 maps from higher dimensional spheres into lower dimensional spheres. Okay. So the version of the Borsuk-Ulam theorem that maybe you've heard about most is that if you map Sn to Rn, two antipodal points need to collide, right? That's equivalent to the statement that there's no Z2 map from a higher dimensional sphere to a lower dimensional one. Okay. So how do I use this assumption on the covering radius to get a Z2 map from the Rips complex into a sphere of lower dimension? So I've assumed that delta is larger than twice this covering radius, which means that there's k closed balls of radius delta divided by 2 that cover projective space. Okay, so here's projective space. It's the sphere, you know, with antipodal points identified. So here's one ball of radius delta over 2 in the projective space. This is the same ball, just the antipodal ball. Okay, so I have k such balls, and they cover the entire projective space. Or equivalently, you know, these pairs of balls cover the sphere. Now, if I take a point in the geometric realization of the Rips complex, well, the support of that point has bounded diameter bounded by pi minus delta. Okay, so let's say these blue points form a simplex in my Rips complex. Their diameter is bounded, which means the blue points can't intersect both this spherical cap near the North Pole and the spherical cap near the South Pole. The blue points only intersect one or the other. Okay, so every simplex intersects at most one of any pair of these antipodal balls. That allows me to define this Z2 function, where if the points intersect the North Pole cap, the value of this function is just the cost I have to pay to move these points out of the blue cap. And then dually, if the points intersect the South Pole cap, I do the same function, but I just make it negative to make it a Z2 map. Okay. Now, these balls cover, if I look at all k balls, they cover the projective space. Okay, so any simplex intersects at least some of these balls. So when I combine these maps together, at least one of these maps is non-zero. So I get a map from the Rips complex to Euclidean space. These k maps for the k different pairs of balls give me a map to Euclidean space. But I know that my simplex intersects one pair of balls, so at least one of these distances is non-zero, so I miss the origin. And then I radially project. Okay. So in total, the proof goes, well, if the Z2 space were sufficiently connected, I'd have an odd map from the k sphere into the Rips complex. Using this assumption on the covering radius, I just produced for you an odd map from the Rips complex to a sphere of one lower dimension. That would contradict Borsuk-Ulam. Okay, so this proof is really due to our collaborator, Florian Frick, right, who's well-trained in combinatorial topology, equivariant topology, you know, Matuseks using the Borsuk-Ulam theorem book. And I think this Borsuk-Ulam machinery is nice. Questions there? All right. I only have 5 minutes left. So let me end with a comments on Gromov-Hausdorff distances between spheres, and then some open questions. And I'll just briefly plug questions about intrinsic check complexes of manifolds. All right, so Lim, Mamoli, and Smith really pioneered this question of what are Gromov-Hausdorff distances between spheres of different dimensions. So Gromov-Hausdorff distance is a way to associate a distance between two metric spaces, and it's complicated to define. You sort of need to infimize over all possible embeddings or matchings between these metric spaces. So since it's defined using a large infimum, it's hard to get lower bounds on these Gromov-Hausdorff distances. They proved some exact values of the Gromov-Hausdorff distances. They proved the exact value of the Gromov-Hausdorff distance between the circle and the two sphere, the circle and the three sphere, and the two sphere and the three sphere. Okay. You notice that some of these scale parameters we've seen before. 2 pi by 3 was when the Rips complex of the circle first changed homotopy type. These RNs were when the Rips complexes of the higher dimensional spheres first changed homotopy type. So we had this conjecture that things should be related to Rips complexes, even though that wasn't known yet. In this large polymath project with 16 collaborators, including Nicola, who's here, we succeeded in connecting Gromov-Hausdorff distances to Rips complexes. So twice the Gromov-Hausdorff distance between a lower dimensional n sphere and a higher dimensional k sphere is at least as large as how much do you need to thicken the n sphere until you do admit an odd map from the higher dimensional k sphere. Okay. Borsuk-Ulam says there's no odd map from the k sphere to the n sphere. But if you thicken the n sphere, then maybe finally there is an odd map going in. So we proved this nice lower bound. It generalized all the previously known lower bounds and improved the lower bound on a general entry. I mean, I think a good conjecture is that this inequality here is an equality, right? So maybe that's naive, but my guess is that this is an equality, that these Gromov-Hausdorff distances are exactly related to Rips complexes. So these numbers in our paper we call CNKs. CNK is how much do you need to thicken the lower dimensional n sphere until you get a Z2 map from the higher dimensional k sphere. I think Nicola will tell you more about them tomorrow. Yeah. Okay, so in my last 3 minutes, let me just advertise some open questions. What are Rips complexes of other manifolds? A difficulty in asking this question is usually we consider manifolds up to homeomorphism, but if you change the metric, you're going to change the Rips complex, okay? Flat tori ought to be considered, so take the flat torus with the L2 metric. You know, nothing is known. Things ought to be known. A little bit is known about ellipses with the Euclidean metric, so that's not the Riemannian metric. For ellipses, symmetry is broken. So these dark equilateral triangles appear before the dotted ones. So it's not a circle's worth of triangles that appear at the same time. It's just two triangles that appear first. And so then, you know, you start with the ellipse and you glue on just two disks to get the two sphere first. So symmetry is broken. But for these symmetric spaces like spheres, there's so much symmetry that maybe you don't need a Morse theory, you need a Morse spot theory. So Morse spot theory is when you have, say, not just isolated critical points, but you have a submanifold worth of critical points, as we saw with the circle's worth of critical triangles. Probably the more natural math question is not Rips complexes of manifolds, but intrinsic check complexes of manifolds. So take your Riemannian manifold and consider all balls of a bounded scale, right? And then take the nerve of those balls. If the scale is bounded compared to the geometry of the manifold, those balls satisfy the hypotheses of the nerve lemma. So you recover the manifold up to homotopy type. But what if the balls get too large? Maybe two balls intersect in a disconnected way and the nerve lemma fails. What are the next homotopy types? So this question is essentially unstudied. For the circle, we know the homotopy types that come up. For n spheres, you take spherical caps in the n sphere. Nothing is known. I mean, this is the regime up to which the nerve lemma holds. once you have balls of radius pi by 2, the nerve lemma fails because the North Pole cap and the South Pole cap, they intersect in a circle, which is not contractible. Nothing's known about the topology until it's contractible. We did get weak bounds on the homotopy connectivity, but somebody needs to figure out what the first new homotopy type is. All right, so let me end there. Thanks. Right. So for the circle, yeah. So I mean, we know that these inclusion maps, if you increase the scale, are always like homotopy equivalences if you don't change the homotopy type, and then they're necessarily null homotopic maps if you do. So this is really the persistent homology bars. This is where the H1 bar is. This is the H3 bar. This is the H5 bar, right? This result would give some consequences for persistent homology, but not necessarily very sharp ones. So let's see if let's say the connectivity of this space is like it's 10 connected, then the first 10 homotopy groups vanish. By Hurevich, the first 10 homology groups vanish. So there couldn't be any, bars of dimension less than 10, at that scale. So this result gives some bounds on persistent homology, but otherwise I don't really know of anything. So that's a good direction. I mean, homology, you could start thinking about cycles, right? And prove things about cycles being contractible, which would be new machinery not yet applied here. Thanks.
Right. I have many questions, but let me just give you one. So if we have, do you think that given a fixed radius, I can expect only sort of simplices of vertex count lower than a fixed number to contribute to the homotopy type?
Yeah, and you'll want to use the metric thickening topology.
Right.
But this would be a good project for somebody to do on the circle, right? So a lot is known about the circle, and there's a lot of machinery, which not many people know anymore. But if you want to learn that machinery, this would be a project that would likely succeed. So let's say your scale is in this 5-sphere regime, right? But let's say you start restricting the dimension of simplices that are included. Now, I'm going to use the metric thickening topology.
Yeah, sure.
But I mean, you sort of proposed this yesterday, right? But if you're removing simplices above dimension 10, above dimension 9, above dimension 8, you're not going to change the homotopy type. It's still going to be the 5-sphere. But then once you start removing simplices of dimension 5 or 4, I think simplices of dimension 4, these regular 4 simplices, then the homotopy type is going to jump down to the 3-sphere. Yeah. I think. And then if you're still at the scale in this regime, if you start removing simplices, of dimension 2, then your homotopy type is going to jump down to the circle, right? Now you want to use the metric thickening topology because if you're using the simplicial complex topology and you remove all simplices of dimension 9 and higher, then you're going to get tons of 8-dimensional homology, right? But just use this other topology that glues things together better. Yeah.
Because if we can get that, we easily get the finite CW complex, finite homotopy type. That would be
okay.
I would worry about.
Yeah, and then of course that's already known in the case of the circle.
Yeah.
Right, but if you could do something analogous for the n-sphere.
Thanks.
Right. So the case of the circle is well understood for Czech. It's not well represented in the literature. We sort of did a hack in the RIPS paper to cheat to get from RIPS to Czech, but a lot of the machinery for RIPS of the circle holds for Czech of the circle. the connectivity, some of the connectivity results, we have analogs for check, right? So connectivity of check complexes of higher dimensional spheres. Yeah. This relates to Lovash's famous result, lower bound in the chromatic number of a graph based on the connectivity of the neighborhood complex of the graph. I mean, in my mind, one of the next questions about check complexes of spheres is just you have say closed balls of radius pi by 2. The nerve lemma fails, but what's the new homotopy type? Right. This is one next question. Another next question would be take the flat torus, two-dimensional torus, draw round balls in the torus, right? Take the nerve complex or the check complex, and make conjectures there. So for the flat torus question with check, to my knowledge, no one simulated it with like take a 10 by 10 grid and then a 100 by 100 grid and plug it into persistent homology software, right? That would be a good first step. You look at the persistent homology of finite samples. Of course, if your sample gets denser and denser, it needs to limit the persistent homology of the check complexes of the actual torus. So could be a good way to start. So I think most of the limitations on check are really just in terms of the literature has focused on RIPS. And that's probably just to advertise it to applied topology community, but check might be the better math question.
Uh, when you start your talk, you mentioned for small scale R, using Lip's complex can recover the original manifold
Mm-hmm.
using sampling, but use studies for every scale R.
Yeah.
So my understanding is there is no absolute criteria which number is small or not. So you studied all scale, right?
Yeah. In unsuccessful grant applications, I motivate this by saying that RIPS are software. We don't know what scale is large or not, so we vary the scale. And we'd like to have better understanding of how persistent homology works than just neural networks, right? Which are black boxes. So that's a good reason to study the mathematics, right? If you have a data set that's sampled from the circle, you will get those homotopy types and persistent homology. And you might be confused and think you have a three sphere where no, it's just because you're doing rips on the circle. Um, but I don't know if I actually believe this work at higher scales is all that relevant for applied topology. What I really believe is that it's nice to connect applied topology to other areas of mathematics. And I mean, I think we've seen a lot of algebra appear in applied topology as from the talks on Monday. And I think there's more opportunities to incorporate more geometry and topology, homotopy theory into applied topology, which would be cool to see more and more of.
Thank you.
To be determined. Yeah. Yeah. Right. So, um, okay, so Lovash was studying chromatic numbers of Borsuk graphs in this paper. Uh, um, so you know what chromatic numbers of a graph are, right? How many colors are needed to color graph. The Borsuk graph, you take an n-sphere and you connect each point to all points at distance at least r away. So a picture. Okay, so let's say we're looking at the Borsuk graph at scale delta. You connect this point to all the points in the sphere, all of these orange points that are at least distance delta away. Okay, and then he asks, what's the chromatic number of these graphs? Okay, and for scales near pi, where each point is connected to most of the points near the opposite pole, the chromatic number is like n plus 2. Okay, so for the two sphere, if you build this Borsuk graph and the scales near pi, you can color that graph with 4 colors. And the way you do it is you color the four faces of a tetrahedron, radially project the tetrahedron to the sphere. Those are your four regions with the four colors. And then, no two faces are, no points in a single face are of the same color are too close to each other. Right. Okay, so I'm giving you a long answer and I'm out of time, so let me get to the point. Okay, so Lovash has this paper where he was studying chromatic numbers of Borsa graphs. He made a mistake in the application to the chromatic numbers. Okay, so there are these funny papers by Ragodorsky where Ragodorsky has sort of funny language, like bragging that he found this mistake in Lovash's paper. I mention this just because Lovash's paper, I mean, most of Lovash's paper have been cited many, many times. This paper has not been cited as much as his other papers. Okay, so what he does in this paper that is correct for sure is he introduces these strongly self-dual polytopes. So you don't have arbitrarily dense subsets of the sphere where the points are equally spaced, right? You don't have arbitrarily dense Platonic solids. But what you do have, Lovash proves, is you do have arbitrarily dense subsets of spheres that form strongly self-dual polytopes. And in these strongly self-dual polytopes, the diameter of the polytope is realized from any vertex. So you see how this vertex has this anti-opposite face? All of these blue edges are the same length, not only for this vertex and its antipodal face, but for every vertex and its antipodal face. So for the North Pole, connected to those 5 points on the pentagon at the bottom, the blue diameter is exactly the same as all these edges. So if you look at the largest distances between these sets of points, all of the largest distances are exactly the same. So if this was a simplex that was going to glue in and change the homotopy type of the Rips complex, you'd probably like deform it, minimize some energy until all of the longest distances were exactly the same length. That would be the first scale at which it would appear. So that's the intuition for why these might change. So what are the strongly self-dual polytopes in the circle? They're all these odd polygons, as we saw. So these are the strongly self-dual polytopes in the circle. And then this is the first strongly self-dual polytope in the n-sphere. This is the next one for the 2-sphere. Right? So Lovash produces an infinite family of strongly self-dual polytopes in an inductive way, inductive on the dimension of the sphere. He probably hasn't found all of them, right? So there have been some recent papers, studying more strongly self-dual polytopes besides the arbitrarily dense one Lovash constructs. But I'd be interested to know more about these. Yeah. Thanks so much.